27 is building off of what we've been working on, is a two-column proof. I've already given you kind of a slight introduction to it. We're going to get away from the algebra style of proofs and move on to more word and geometry-based proofs. So again, our proofing system will have two columns. We'll have a statements and a reasons column. So our statements will be on the left, and our reasons will be on the right. Okay, so whatever we're stating is obviously going to be in the statements column. Now the reason we're stating it is going in the reasons column. So a lot of these, like on example 1, they'll give you the statements and tell you to provide the reasoning. Okay, so they normally base off of some theorem or something that we've already went over. Theorems, postulates are the most common thing you'll see. So to follow the example, you have to first read and then go from the picture. So let me go off the picture real quick. It has A, it has B and C. A, B, and then C is off of the line. So it says fill in the justifying statements to support the proof of Theorem 4.2. Theorem 4.2 says if there is a line and a point not on the line, then exactly one plane contains them. Every single proof that you will do through the Saxon book for us, pretty much the very first thing that you see is a given, almost every single time. So it says point C, this is number 1, okay, it's already filled in for us, so I'm not going to rewrite it. It says point C is non-collinear with point AB. Okay, and looking at that, we can see from the drawing that that is given to us. It says it's non-collinear, meaning it's not on the same line. So almost always, the very first thing that you will see is a given statement. Next, it says exactly one plane contains points A, B, and C. Remembering the definition of a plane is 3 non-collinear points create a plane. Okay, so on number 2, we would basically just state the definition of a plane. So if you remember the definition of a plane, it's 3 non-collinear points. There's exactly one plane. So I would literally just state definition of a plane for number 2. And then number 3 says exactly one plane contains points A, B, and C. And this would be a therefore statement. Okay, it says therefore exactly one plane contains it. So if 2 points are in a plane right here, then the line containing them is also inside of that plane. And there's a postulate that states this definition. If you don't know the postulate, then you have to restate its definition. So you would literally write it out. I didn't memorize the postulates. I don't expect you to memorize the postulates, but you do need to have them. So this one was postulate 8, but you need to know the definition. This is if 2 points are in a plane. So if 2 points are in a plane, then the line containing them is also on that plane. So most of the things that you're going to put in the reasons column will be definitions of some sort. Whether you're writing them, whether you write the definition out, or if you can write a shorthand version of it, that is fine too. I just have to know what you're talking about. Okay, so it doesn't matter too much to me that you know postulate 8. That isn't going to do you any good. I don't know what postulate 8 is because every single book has a different postulate 8. So you can't just base your knowledge of it off of postulate numbers or theorem numbers because they change depending on what book you're in. So that was example 1. I don't like that they started with that example. So example 2 is a little bit better, and I expect you guys to ask a few more questions here on example 2 just to move this along a little bit faster. The statements are given to us, so I'm not going to write the statements column. I'm just going to leave a little blank for it and write 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And as I said before, the very first thing that you will normally see in your reasons column is a given. Okay, it was given to us. So number 1, notice that it says on example 2, it says it right at the top. It says that it is given. Given. Angle 1 is complementary to angle 2. Angle 3 is complementary to angle 2. So both of those statements are given. So when we start moving down into our proofing statements, look at the very first thing that you see is your givens. So you restate your given, you write that it is given, and then you start with your progression down the line here. Okay? If 1 and 2 are complementary, then that means that they're equal to 90 degrees when added together. If 3 and 2 are complementary, that means that they are equal to 90 degrees when they are added together. So that is just telling me that the definition of complementary angles allows me to do that. So on number 2, I would write definition of complementary angles, and then that just allows us to substitute those two properties in. So the definition, and I always write def period, of complementary angles. Next, it says that they're equal to each other. What tells me that I can set these two equal to each other? It's because of the 90 degrees. Okay, these two 90 degrees here allow us to set them equal to each other. That's a substitution right here. If this one's equal to 90 and that one's equal to 90, then they must be equal to each other. So that's a substitution property of equality. Don't just write sub, because that could be subtraction. So write out the word substitution. And then you can use the abbreviation for property of equality, that's fine. On number 4, it shows you what it changed. It says it subtracts 2, the measure of angle 2, from both sides. So if I'm subtracting something from both sides, that's the subtractive property of equality. So subtraction property equality. Property of equality. So you're just looking for what changes in between each one. So they combine this one, they combine this one. What's left is the measure of angle 1 is equal to the measure of angle 3. All they did was simplify, basically. So on number 5, all they did was simplify. They combine like terms, in other words. Instead of saying combine like terms, we'll say simplify. And then they always throw in this step, and I won't count you wrong if you don't throw in this step. All they do is take out the measure symbol and set them congruent to each other. Instead of saying the measures are equal to each other, they change it to they are congruent to each other. And all that property is, when you change from measure to congruency, is just a congruency property of equality, is really all it is. So it's the definition of congruent angles. So when you write your own proofs, I don't necessarily expect you to write that part, but since the question does ask us to prove congruency, we have to simplify it and then show that that congruency changes over. So it's just a definition of congruent angles. Two angles that are congruent are also equal to each other. Definition of congruency. Definition of congruent angles. Now, I wish there was a solve all and hey, you're going to understand this the first time around and there's no way you're going to get it wrong. I'd be lying to you if I said that was true. I made it through almost 3 years of high school math before I had a pretty good grasp of what I was doing when I wrote a proof. So no, you may not get it the first time. You may not get it the second time or third time. But if you continue to trudge through these slowly and ask questions, you will get them eventually. Okay, the more questions you ask, the more likely it is that you'll get them faster. Okay, so don't be afraid to ask those questions. Just as for what's going on in the reasons column, do I have any questions that need to be answered yet? Speak now. Okay. There are 5 parts of a two-column proof. 2 columns literally just means it has 2 columns, a statements and a reasons column. There are given statements. Like I said, it's the very first thing you'll normally see. And then the prove statement, which is the thing you'll normally see at the very bottom. It's what we proved. So in this one was step 6. Then in number 3, there's normally some kind of picture that goes along with whatever we're talking about. It's a diagram of some sort. So there'll be a sketch or something that'll help you along your way. And then obviously there's going to be a statement, and then there's going to be a reason. So those are the 5 things that I'll be looking for when I grade your proofs on your tests. Okay? There'll be a given, there'll be what you proved, and I'm going to make sure there's a logical flow from the given to the proof to the end of the proof. Your diagram will be given to you. Okay, and then you need your statements and your reasons column. And you always need those as titles. Okay, consider those like titles. Okay, flip the page, or look at the next page, I guess. On example 3, it gives us a 2-column proof that we need to write. So, looking at example 3, and I know that you can just look at the solution. I see the same thing that y'all guys do, but we need to figure out how they arrived at the solution. So we're going to have to set it up. Write this all the way out. Practice it with me. Statements and reasons. That's the very first thing you need to write. Statements and reason. Okay, so the very first thing is what was given. Our givens were AB, line AB, and DE. So those two lines intersect at a certain point. Intersect at point C. Okay, that was our given. And there's a diagram that they give us to go with it, but I'm just going to draw it really quickly. They intersect right here in the center. Okay, so from that, I need to get to a point that proves that angle ACD and BCE are congruent. Okay, so I need to get to a point where I can say that two angles are congruent. So what I do when I do my drawing is identify what I am trying to prove. So when I read it and it says angle ACD, this one right here on the left, needs to be congruent to BCE. Okay, I know that I can get from the original drawing to this drawing by knowing what is basically what I'm getting to. What are these two angles called? You guys remember? They're straight across from each other. If I turn them straight up, they are Nope. Vertical. They're called vertical angles, a definition that you've seen since 7th grade. 7th. So vertical angles are across from each other. Okay? So ACD is across from ECB. And the same thing goes for ACE and DCB. But those aren't the angles that we're looking at. But you need to get comfortable with that definition. I've given it to you about 20 times. We need it. Okay, so I think that we're going to end up using vertical angles at some point in this proof. So again, these are very, very long and drawn out. And some of the things that you state, you're going, well, this is obvious. You don't have to state that. Yes, you do. Okay, you have to state even the most obvious things. What did they call them? A few years ago, my sophomores called them idiot guides, basically. If you were explaining this to an idiot, what would you tell them? So basically, that's how it goes.
I say, hey, Mr. President, how you doing?
How wise of you.
So it's just kind of like a liberal guide. Is what it is.
There you go.
Yeah.
Liberal guide. According to law. Okay, so moving on. I need to go from what I know here, that these intersect, and I need to get to eventually saying that my angle ACD will be congruent to angle BCE. So this is how I write them. I make a big gap and then I fill in the gap, knowing that from one destination to the other I need to get to. So I want you to look at BCD and ACD. What do I know about those two angles together? They're on a what?
180.
They're on 180. So I know that the measure of those two will be 180 degrees because they're on a straight line, right? They're a linear pair is what that's called. So the measure of those two angles, it was BCD plus the measure of angle DCA is equal to 180 degrees. And nobody argues that point. We know that that's true, right? Why do we know it's true? It's because it's on a straight line. That's called a linear pair. So it would be the definition of a linear pair. When two angles create a straight line, it's called a linear pair. And we'll use definition of a linear pair a lot, so get used to that one there. Next, going from what I knew about these two angles, creating a linear pair, I can also see that this line here, DCE, is made up of two angles, DCB, measure of angle, I'm going to say it like this, BCD, instead of DCB, because if I look at the one right above it, now they look the same, even though they're the same angle, right? Plus the measure of angle ECB, and nobody's going to argue that that is 180 degrees because it's a linear pair. If I have the same thing stated above, I'll just put the quotations to say that that is the exact same thing as it was above. Okay? Now, there's a definition somewhere down the line that we learned. It said, if an angle is complementary, if two angles are complementary to the same angle, then those two angles are equal to each other. Okay? If two angles are complementary to the same angle, then they are equal to each other. And there's another one that said, if two angles are supplementary to the same angle, then those two angles are equal to each other. So here, because it's 180, am I talking supplement or am I talking complement? Supplement, right? Because that one's 180. So I think that I'm going to use the definition of supplementary angles here. It's either that or vertical angles. So I'm going to go with, hopefully, supplementary angles. Because that's what I'm starting to prove right here. Since these are both equal to 180, so look back at your last page. Look back at your last page on step 2. See how these were both equal to 90? These are both equal to 180. Look at the next step that they did. They set them equal to each other. Most of the proofs that you see in your lesson are going to be really, really, really closely related to the ones you see in your examples. Okay, so use them. So if these two are equal to 90 and these two are equal to 180, then I could probably set them equal to each other. Okay? So since these are both equal to 180, I'm going to set them equal to each other. I'm going to need a longer line. So the measure of angle BCD plus the measure of angle DCA, I'll just copy that, equals measure of angle BCD again plus the measure of angle ECB. Okay, what allows me to do that? The substitution property of equality. Substitution property of equality. Okay, before I go on to the next step, I'm going to let you guys catch up. 1, 2, ask questions. You got to have questions, guys. Okay, from here I'm going to start to solve. I notice that this and this are the same, just like it was here. See, they had angle 2 in both of these, so they subtracted angle 2 from both of these. So here I'm going to subtract angle, the measure of angle BCD from both sides of the equal sign. And if I'm subtracting something from both sides, what allows me to do that is called the subtraction property of equality. So the next step here is the subtraction property of equality. Okay, so that is what allowed me to do the subtraction from both sides. Okay? These get eliminated. These two go away now. All I'm left with is the measure of angle DCA being equal to the measure of angle B or ECB. Okay, let's look at angle DCA. DCA is right here, and ECB is right here. So I've proved what I've needed to prove. Just because this says BCE and not ECB doesn't mean they're not the exact same angle. Notice that the C is the same and the end letters are the same. Okay, same concept goes here. These are the exact same angles. Okay, that's just simplification. Simplify. And since I had measures here, when I convert from measures to congruency, it's just the definition of congruent angles. And most commonly, what ends up happening is y'all guys are confused on what to do. The main point is that I want y'all guys to be able to write down your reasoning for them. Okay? So if you get stuck somewhere, you're like, I don't even know where to start, then I can get you started. But you have to finish by yourself. But I can get you started. So that's a question that you'll just have to ask. If you don't even know where to begin, which most of you won't, at the start, you just ask, and we'll get it figured out. Okay. All right. That was example 3. I want you to look at. Whoops, sorry.